not the original one. So it will go back to x squared. So it would just be 0, 9. And now we put those. Yeah, look, it's the same side. Oh yeah, this one's good. So yeah, this one, so this one's should be.
All right. Don't you? I thought you plugged into F, not F prime.
Where?
Yeah, we was discussing that
So
too.
you plug into when you get your critical points. I thought you plugged them into the original equation with the x squared.
Where did I put them? Oh, I put them, yeah, I'm sorry. This is 9? 9, sorry, 9. Yes, thank you. All right. So did you all have any trouble with the first part, L1? Anyone question? So here we're just going to have a function of y instead of x. So we still do the same thing, take derivative and all that. Same idea, right? So when you plug in 0y, 0 for x, you just get what? Oh, 2y, it's linear. So you just have to evaluate the two endpoints? Right, that's linear? So you just evaluate the two endpoints. So you don't even need a derivative or anything, just 0. 0, you already did that, right? 0, and then when you do 0, 2, you get 4. All right, how about this one? At x2, that looks crappy. That's quadratic, isn't it? So when you, I'm going to erase this one. So when you go f of x2, what do y'all get when you do f of x2? X squared, 4x plus 4. Okay, so that's our function. We have to take the derivative of this now, right? Set it equal to 0. So take the derivative, set it equal to 0. So 2x minus 4, set that equal to 0. You get a solution of x equals 2. And so what I want to do is I want to evaluate this function. This is my function f, right? F of x. I want to evaluate that at 2 and at the two endpoints, 0 and 3. So if I plug 2 into this, not the derivative, into this, you get
No.
0, right? You get 0? 0? What is it?
Oh yeah, yeah.
I think you get 0. When you plug in 0, you get 4. When you plug in 3, you get 1? Okay. Oh, I haven't been putting my points over here. I'm sorry. I forgot. Okay, what were the points here? 0, 0, 0, 3, 0, 9, 0, 0, 0, 0, 2, 4, 2, 2, 0, and then, you know what I'm doing here? 2, 2 goes here, 2, 2, I get 0, 0, 2, I get 4. Do I have that over there yet? Yeah, I already have that. 3, 2, I get 1. I don't think that's over here yet. Does it make sense? Going kind of quick here, but any questions? All right. One more, right? One more, L4? Okay, so L4. Points there looked like 3y. Y was between 0 and 2. Okay, so when you plug in, what did you get when you plugged in 3y? Did anyone get to that yet? 3 for x, 9 minus 2 times 3, 6y plus 2y. Linear. Yeah, linear. Okay. 9 minus 4y. Since it's linear, I just evaluate the two endpoints. So I get f of 3, 0, and f of 3, 2. I think I already have those over there, don't I? Yeah, I do.
Yes.
I do. Over there. Yes, what is it?
Let's go back to L3.
Yes. Uh-huh.
Okay.
We found derivative.
Okay, yeah, we plugged this in and we got a quadratic. We said, okay, we got to find the max or min of that quadratic on this closed interval. So we take its derivative and set it equal to 0.
Yeah.
Solve that, and that's one of our critical numbers.
Okay.
We need to plug that into this
Okay.
and the two endpoints into this,
Into the polynomial.
into this right here.
Okay.
And that will give us the maximum minimum values of this right here, right? Okay?
So how's f of 3 1?
I don't know. Someone said it was 1.
I got 5.
9 minus 12 plus 4.
9 minus 3,
That's 8.
4 times 3 is 12,
Oh.
right?
I see what
You're
I
plugging, yeah, you got it?
Yeah.
Okay.
Okay. It's very confusing.
And then do you understand why this right here becomes 220?
Yeah.
Yes?
Uh-huh.
Because the x is 2, right? But the y is 2 as well.
Yeah.
And then this is 3, 2, right? So this is 2, 2, 0, 2, 3, 2.
Yeah.
Okay. All right, so what is the absolute maximum value of this function on this closed bounded region? 9, right? And what is the minimum value? 0, and it happens at 2 different places. Okay. So far, do you get the general idea of how to do this?
Yes.
Yeah? What do you like, this more or the calculating D that we did last time where you find local max? D? Yeah?
I feel like this has got to go somewhere else, so this can't be it.
You're right. Shall we look at it? Let's take a look visually just to see what it looks like. Here's the original surface. If we don't restrict the domain, that's the original surface. Here's the domain in 2-dimensional space. Here's the domain in 3-dimensional space. Here is the surface not restricted. Here is the surface restricted. I'll take the other surface out. So that green little like sheet, we're trying to find the absolute max and min on that sheet. Anywhere on the edges or in the middle. And we determined that we have 1 maximum point and then 2 minimums. Okay?
How long did it take you to program all this?
I don't remember. I mean, I spent a lot of time, but I've kind of figured you make it once and you won't have to make it again, you know?
Yeah.
Code for this one's not that bad. I mean, it's there, right? But this is still way more powerful than what I can do on Desmos, and you know, I have a lot more control here. All right, let's see if we have another one. Yep, there we go. Find the absolute maximum minimum values of the function f of xy is xy squared on the region D equals the set of points xy such that, first, your x has to be positive, or sorry, not negative, greater than or equal to 0. Your y has to be greater than or equal to 0. And x squared plus y squared has to be less than 3. What is that? X is greater than or equal to 0. Part of a circle. It's only, the x has to be greater than 0. So we have to be this way, right? And then y has to be greater than or equal to 0. We have to be up here. And then x squared plus y squared less than or equal to 3 is a circle, right? So isn't it just a circle like the first quadrant of the circle like this? And then this boundary here like this. Everything in here, this is D. Now, what is the radius? Root 3, good, careful, right? Not 3, but root 3. All right, let's start with step 1, which is critical points, right? Let's find our critical points. So how do we do that? Take the partials, right? So for the first step, I want my critical points, and I take my partial with respect to x, set it equal to 0. And I do my partial with respect to y, set that equal to 0. With respect to x, we get what?
Y squared.
Y squared. equals 0. Well, that already has a solution, right? Y is 0. And then here, partial with respect to y, 2xy equals 0. But wait a minute. But y has to be 0. So x is what? Well, x being 0 is one possibility. Could x be 1? X could be anything, couldn't it? But wait a minute. It has to be positive, right? It has to be positive. So what the hell is this? Hold on. Do y'all understand that this right here just turns into 0 equals 0?
Yes.
So really what we have is this. We have any point that satisfies this. The x can be whatever it wants to be, and the y has to be 0, right? The x is free, right? This is what we call a free variable. This is a free variable. X can be anything it wants. The y has to be 0, and that's going to be a critical point. But that's just anything along the x-axis, right? Isn't it actually everything on this line segment right here? Okay, so you know what? I don't need to look at that anymore because I'm going to take care of that when I move around the boundary. See what I'm saying? Like, I don't need to consider this because that's already going to be my, what you want to call it, L1? Call this L1. This will be L2. And this will be C1. Curve 1. Because L was line, right? That's not a line, that's a curve. So it would just be a little silly to me to call it a line. Line 1, line 2, curve 1. So this right here basically is going to be covered with L1. So not considering this because L1, right? We'll cover that case. All right, let's do L1. So now we're going to move along the boundary. BND, boundary. So L1, anywhere along L1 looks like x0, except there's a restriction. X has to be between, what, 0 and root 3? Okay. All right, what happens if you plug x0 into the original function? You get 0. Which means that along this edge, any points along this edge, your surface is what? Down on that axis, right? Your surface like bends down, or bends over, curves down, and touches the x-axis everywhere. So I don't have to write anything else. That could possibly be a max or a min. I'm going to move on to L2. L2 looks like 0y, but my y has to be between, well, 0 and root 3 again, right? Okay, but what does the function look like along that? What happens when you plug 0y into the original function? You get 0 again. So, hey, look, along that side it's 0 as well, right? Do y'all want to see it? Let's look at it. Here's the surface, here's the domain. Here's the original surface. There it is. Now I'm going to restrict it to that little quadrant, first quadrant piece. Take the surface back out. Do y'all see the green surface there? Yeah. Do you see that the edges along the axes, the x and y axis, do you see they just touch along the axis? Okay, that's what we just determined. Hope that makes sense to you. All right, so now what? C1? Okay, let me erase this. I'll move along C1. So along C1, well, then I'm working on that circle, aren't I? I'm working on the circle. I'm moving along the circle. And the equation of that circle was x squared plus y squared was equal to 3. And to get the actual curve, to look at this as a function, I need to solve this for y. If I solve that for y, I get plus or minus the square root of 3 minus x squared, right? Subtracting x squared on both sides, taking the root, and I'm only going to look at the positive answer, right? Because the positive answer, the positive draws me the top half, the negative draws me the bottom. So what does every point on that curve C1 look like? The x is what? What's the x coordinate? So if I pick a point here, right, call it x, then the x coordinate is x, right? It's whatever x is, right? And what's the y coordinate? Square root of 3 minus x squared, right? And what's my restriction on x? 0 to root 3. Do y'all see what I'm doing? This is just like in the previous one. Remember when we had a line, we had to find the equation of the line, then we solved it for y, and then that became the y coordinate? Same exact thing, except our y coordinate now is not, it's not linear, it's a square root. Okay, took the equation of the circle, solved for y, plus or minus, only looking at the positive for the top half. Now, what does my function do when I plug that in?
3x minus x cubed.
Yeah, thank goodness, right? Thank goodness it's going to be x, and then I take the square root of 3 minus x squared, and I square it, right? And that just makes it x, and then 3 minus x squared, and that's 3x minus x cubed. That's not linear. So I'm going to have to take derivative, right, and do all that stuff. So let's take the derivative of this, treating this like my f of x. Take the derivative, set it equal to 0. What's derivative? 3 minus 3x squared. Set that equal to 0. 3 equals 3x squared. Divide by 3. X is plus or minus 1. But I'm going to throw away the minus. Why? Because I'm only to the right. Okay, what else? Don't have to check the endpoints? Yes? Okay. So in blue, this is the thing I'm treating right here as my function, f. I'm now going to take my f and evaluate it at 1, my f evaluated at the 2 endpoints. Okay, when I plug 1 into this, I get what? 2. Plug in 0, I get 0. And then root 3 is a little weird. 3 root 3 minus root 3 cubed, which is 3 root 3. Wait, is it? Yeah. This is 0. If you don't like that, then you could have taken this and factored an x out, and then you would have got this. And now you can see if you plug in root 3 squared is 3, 3 minus 3 is 0. So either way, you should get 0. Okay, so have I listed any points? I haven't listed any points, have I? How do I list these points? Let's do these first. What are the points here? I have, when I plug in 1 for x, right? What's my y coordinate when I plug in 1 for x? If I plug 1 in for x, we're plugging it in right here, right? 1, and then right, yeah, you get root 2. And what happens? I get 2 to come out, right? Then when I plug in 0 for x, I get, what's my y? Root 3. And my z, my z is 0. And then when I plug in root 3 for x, I get 0 for y, and then 0.
How do you,
Yeah.
can you explain how you get your y values, please?
Well, there's a couple of ways to do it, but I'm really just picking them off from here. Because this is what happens when I plug in 1 for x, right? So if I put a 1 here, and then plug that 1 into this, I get root 3, right? Where is it? Oh, sorry, root 2. Right? If I plug in a 1 here, I get 1. Plug in 1 here, I get 3 minus 1, that's 2, root 2. So that's 1 root 2. And then how do I get the 2? I can either look here, or I can actually just plug 1 and 1 into this. And that'll give me the same answer. Oh, no, wait, yeah, before the derivative, yes, right there. Or, yeah, you don't want to use that one because I just say use this. All right, can we answer the question yet? What's the absolute maximum value of this function? 2. Where does it happen? At one place, right? What's the absolute minimum value of this function? 0. Where does it happen? A lot of places. Actually, all along the x-axis part here and all along the y-axis part. So we'd really be more interested in just saying where it happens. I mean, not where it happens, what it is. Maximum value of 2, absolute minimum value is 0. All right, I showed you the picture already, right? Showed you that picture. You can see we have one maximum there. And just ignore the 3 dots on the bottom. That's not, it's the entire edge. Hold on. Let me think for a second here. Yeah, I don't want to do this problem yet. That's it. That's it for 11.7. And those are the homework problems. All right, so we're at a weird spot here because it's 12:03, and we have plenty of time to start Lagrange. All right, and we still have next week, right? We have Monday. Our test is on Wednesday, so y'all ready to start?
Yeah.
Okay, good. Remember, okay, so from right now, from what I started right now, is not on the test. All right? What we just ended with is, but starting with this next section will not be on the test on Wednesday. All right? All right, this is usually Cal 3 students. They love this section. Absolutely. All they want to do is keep doing Lagrange for the rest of the semester. I have to push them into the next chapter. I'm being sarcastic, obviously. So, look, the idea here is weird. Like, it's hard to explain geometrically. I'm going to try why this thing works, but it's hard to see, all right? So that's number one. It's hard to visualize what's actually going on. And then the other part that's difficult about it is that we're really going to be tested in terms of how do we solve systems of equations, which we've all seen systems of equations in college algebra and also in linear algebra. But those systems of equations are linear equations. You have like x, y, z, and the x, y, and z are always raised to the first power, linear, right? We're going to be solving equations that are nonlinear. They're going to be systems of equations that are nonlinear. So it's going to be a little bit harder, a bit harder. And the only way to kind of get comfortable with it is to see, like various approaches. I might do it one way, you might do it a different way, you might do it a different way, you might do it a different way. There's not one right way, as long as we all get to the same conclusion. So that's what makes it hard. There's many different paths you can go down, right? So I'll try and show you enough that you feel comfortable at least wanting to go down a path, all right? But it's impossible for me to show you every variation of how to solve something. All right, so what is it that we've done so far? All right, let's do a little recap of what we have up to this point, right? We can find the local maximums and local minimums in saddle points of a function on its implied domain. So that's, if we're not restricting the domain down to like a closed bounded set, we can find these like humps, right? The valleys, hilltops and valleys of our surface. And that we use the computation of capital D, right? Then what we just did in the next part of that section is we said we can find the absolute maximum and minimum of a function on a closed bounded region. And for that we had to do some critical points, and then we also had to move along the boundary and find maxes, mins. All right, that we got covered. We now develop a very powerful method for finding the maximum and minimum values of a function subject to a constraint. Subject to a constraint. So I think the easiest way for you to understand subject to a constraint is if I go back to the problems that we just did with the boundaries. Imagine we were asked to find the maximum and minimum values of that function just along the boundary, not on the inside as well, just the boundary. That boundary would be considered to be a constraint. So instead of your domain on the ground being a closed bounded region, it's just the boundary of a closed bounded region. Make sense? Just along the edges. The Lagrange method is how we can find max and mins just along that boundary. So here's the actual method. And when you see it for the first time, you're like, okay, whatever you say, man. All right? So first we're going to start with how we do this if we have two variables. In other words, our function is a function of two variables, f of x, y. So somebody gives us a surface, right? Some surface. And then they give us a constraint. Now this constraint is a constraint equation, all right? And I'm going to show you some examples, but I want to show you like visually just off to the side here what I mean while I talk about it. So if I say f of x, y, that's some sheet like floating in the wind, right? In three-dimensional space. If I say I'm going to take that and I'm going to make this function be subject to a constraint, this equation right here would be something like, I don't know, I'm just going to make up an equation. X squared plus y squared equals 1. Do you all see that if I write that, g of x, y equals a constant? Do you all see that right there? What does x squared plus y squared equals 1 look like? It's a circle in two-dimensional space. In three-dimensional space, it's what? A cylinder, right? So either way, however